Hello, today is November 5th, 2014, and today we're going to go over part 5, the last part of the new astronomy, and see if there's any questions about that or any other part of the book. So, I guess I'll just start talking about part 5. It's been a few weeks, so it might be a little bit rusty what Kepler's been up to, but part 5 is on latitude, which, if you think about it, latitude hasn't really come up in the book for a long time. In fact, can anybody think of the last time they remember Kepler talking about latitudes or using them for anything? I guess not. Well, in part 2, Kepler would use the latitudes to show why the vicarious hypothesis couldn't work. But since then, they haven't really come up at all. Part 3, latitudes just don't really matter. In part 4, latitudes don't come up. In the vicarious hypothesis itself, there's no thought about latitudes or inclination. Everything so far in the book has been dealing with longitude, the planet moving around the ecliptic this way. We haven't looked at all about it moving up or down. So that's going to change now because that's what part 5 is about. So there's a couple things that make this part of the book pretty interesting. For one thing, you might say, why is it treated separately? Because all through the book, at least in part 2, he had found where the nodes were, which is where Mars's orbit crosses the ecliptic, where it has no inclination. He found how inclined it was. And the vicarious Kepler had already done that back in part 2. But the other really big aspect of this is that his theory of the latitudes is so simple. I was looking up a little bit about how the other people had used latitudes because it's sort of confusing. I don't actually understand really how any of the three before him. I don't understand their full theories of latitude. But here's what I read about Copernicus's. He says for the inferior planets, Mercury and Venus, the deferents are inclined at a varying angle. That is, the deferents of Mercury and Venus constantly change their angles to the ecliptic along two axes at once, with the result that Venus is always north of the ecliptic and Mercury is always to the south. That is, Copernicus, and this is not talking about the motion of the nodes, just that during the year, the inclinations, the way that they're tilted, changes all the time. For Copernicus, the deferents of the superior planets were inclined to the ecliptic at a small angle, which varies in time with the mean sun. Again, a very odd thing, that the inclination, Copernicus, for one thing, it changes, and that it's connected to the mean sun or the Earth again. So there was no simple understanding of latitude. For Kepler, it's incredibly simple. Kepler makes the orbit. He's found out at the end of part 4 that a planet moves in an ellipse. That the planet moves in an ellipse, that it sweeps out equal areas in equal times, and Kepler just says take the orbit and tilt it. Now it's inclined. That's it. It's that easy. No one else had such an easy approach to latitudes before him. So that's one thing that makes this part polemical, is that its simplicity. The other aspect of it is that there's one more aspect of geocentrism that Kepler has to remove, which is even the language used to describe where a planet is. When we make an observation of a planet, you might talk about it in terms of where you see it, of right ascension or declination, but when you refer it to the ecliptic, you've now given it measures of longitude and of latitude. The distinction between them, of course, is that longitude is moving along the ecliptic, along the general motion of the planet, and latitude is above and below, off of it. But the ecliptic itself, on which the longitudes move and against which the latitudes are measured, it's just the motion of the Earth around the sun. So while we've been pursuing these planetary theories, we've constantly been introducing the Earth as a basis of measurement the whole time. We've never actually measured any planet's inclination with respect to anything besides the Earth. So you might say, well, what else would you measure inclination against? If you're not going to use the Earth, as the basis for what you would call 0 degrees of inclination, what is? What's the basis of, is there any physical basis for having longitude versus latitude? Can anybody think of a physical basis for separating longitude and latitude? What makes them different besides, without having to base it on the Earth's orbit around the sun?
The axis of the sun's rotation, although I guess they probably couldn't have seen that at that time.
Right. Well, yeah, you're right on both of those. Yeah, Kepler says, let's make the real measure of longitude. Let's say, how's the sun spinning? And then it spins out on a plane. That's longitude. That's the, like a real ecliptic. Kepler ends up calling it the Royal Road. And, if you go above or below that, that's latitude. And you're right. No one had seen the sun spin. A sunspot had never been observed before. In fact, Kepler saw a sunspot, and he didn't think that's what it was. He was doing an experiment where he was trying to watch a transit of Venus, when Venus passed in front of the sun. And he was using a sort of a camera obscura. He was in a house where the boards in the roof left a small crack, and so it made a projection on the floor of the sunshine. And he saw a spot on the, in the image made by the sun, which he thought was Venus. It was a sunspot. It wasn't Venus, but Kepler didn't know that. So yeah, before there was any inclination that the sun moved, which came from seeing sunspots moving, which gave, with sunspots, you can actually have a hypothesis of how the sun's spinning. What its axis is. Is it spinning with the planets? Is it spinning in a totally different way? Is it spinning the same direction? You wouldn't be able to really do any observations to know anything about that before sunspots. And so Kepler, without any observational evidence for it, hypothesized, as he's been saying, that the sun is spinning, that motion is connected or related to the motion of the planets, and that would be the real basis against which, a physical basis against which you'd measure latitude. So yeah, absolutely right. So here's the trouble. How do you think he might, any ideas about how we could find what that other ecliptic would be?
Well, maybe you could compare the, because Kepler directly correlates the speed at which the sun rotates. He says that that's also determined by the physical principle of the solar system itself, and he does a particular calculation for how fast he believes the sun would be rotating. So if he took like one orbit, say the orbit of Earth, and calculated how fast it was rotating, and then looked at the orbit of Mars to see how fast it was rotating, and then compared it and saw whether or not the orbit of Mars was faster, was it maybe just a tiny bit faster or maybe a tiny bit slower than would be implied by the difference in its distance from the sun is calculated from the Earth, and maybe from that he could say, oh, wait a second, the Earth is moving a little bit too slow, or the Mars is moving a little bit too slow or too fast.
Mm-hmm. And what would he, and then how would he, where would he go with that? I follow what you're saying, and then how would he then use that to take the next step and be able to hypothesize an orientation for what the real ecliptic would be? What orientation the axis of the sun spinning has?
If he, I'm just trying to think it through in my mind. I'm not sure exactly how, but if he were to look at Mars, for example, and determine the speed of Mars's orbit, which you can do, with a simple calculation, and then compare that speed to, well, you'd compare it to the distance. You compare the differences in the speed to the differences in the distance from, in one case, Earth to Sun, and then Mars to Sun. Compare those distances, and then maybe also taking into consideration, the latitude, and seeing. Yeah, I'm not sure. I'm not exactly sure.
Keep thinking it through. What you're describing is not what Kepler used to make a hypothesis, but it's something that he could have used. I mean, it seems like keep thinking it through, but to add something to it, it seems like you might be able to, if you found that there were parts on the planet's orbit where it went unexpectedly fast or slow in a way that wasn't related to the ellipse, but there's some longitude where it seems to be moving faster. Like at this place and this place, it goes a little bit faster than you would expect based on its, the ellipse and area time. You might say, maybe that's right when it's passing through the plane of the sun's rotation. And if you saw it went a little bit faster there, and then based on the inclination of another planet, you might be able to start piecing together that there is in space a plane where things go generally faster, and when they come up out of it, they go a little bit slower. So,
that seems a little bit easier.
Oh, that was my impression of what you were suggesting doing, actually. But well, here's the thing: is that if there is such an effect, it's very small, because Kepler, with the ellipse and area time, it basically works. To any precision that Kepler had, it works perfectly. So that wouldn't work for him as a clue, because if the planets do slow down when they come outside of this plane of power of the sun, then it's too small to show up in the observations that he's got. So he has another hypothesis, another way of trying to figure out what the physical ecliptic would be. But first, let's before we get there, that's chapter 68 and in this part where he lays out a way of getting it. Let's just talk about what happens earlier in it. Now, there's a Google Doc in the video description, and that pretty much gives a summary of the part. So I don't feel the need to repeat all of that. They're very short summaries, and a lot of it's pretty straightforward. The first couple chapters of the book are finding the nodes, which is very easy to do. You just look for when does the planet have no latitude? When does the planet not look like it's north or south? Well, that's when it's at its node. So you just find out where that is. Not so hard. Just to get the terminology, then, because we've got a bunch of words about orbits that we've already been using frequently. So apsides, eccentricity, aphelion, perihelion. Those are some words we've been using. The terminology for latitudes, there's basically three terms that we need to know. One is the nodes. So if we have the ecliptic, the Earth's ecliptic, the place where Mars's orbit intersects that would be the nodes. The nodes are where a planet has zero latitude, zero inclination. Inclination is how tilted is the whole Mars orbit in comparison with the Earth's, with the ecliptic. That's the inclination. For Mars, it's almost 2 degrees. It's 1 degree in 50 minutes. And then the third term is latitude. Latitude is where we observe the planet to be. So just like the sun sees the planet in a certain constellation, even when the Earth sees it in a different one, there's the longitude from the sun, there's our measured longitude when we make an observation. The same thing with the latitude. Where the sun sees the planet in terms of how inclined, how tilted up it is, that's the inclination. And where the Earth sees the planet, the amount north or south, that's called the latitude. So in chapter 61, he finds the nodes, piece of cake. In chapter 62, he finds the inclination. Again, it's very easy now that he's got area time and the ellipse, and he knows exactly where Mars is. So finding the inclination is easy, and he already had it basically. The numbers that he got for the inclination back in chapter 17 they match these great. So he had already done a very good job of finding the inclination. He tests himself by recomputing what the latitudes would have been in those 12 observations that he uses, the opposition observations. Just like he compared the vicarious hypothesis to the longitude of all 12, he compares his latitude model idea to all 12, and they're all within a couple minutes. Then he's got a physical hypothesis for what's causing the inclinations. So this we're going to talk about. I'm going to switch the view here to the paper and take a look at this physical cause. So going back to chapter 57, Kepler had a hypothesis for why the planet would get closer and farther from the sun. So with this orbit here, let's just mark a few of these spots. So this is the aphelion. This is the perihelion. And right here, these are the mid-longitudes. Kepler's hypothesis in chapter 57 was that there was a force like a magnet that maintained its orientation as the planet moved around the sun. So what he'd say is here at aphelion, the planet's moving this way. The magnetic force, here the direction of the marker, is pointing more towards the sun than away from it. So the planet is becoming closer and closer and closer to the sun. Now here it's really pointing towards the sun, so it'll keep getting closer. I didn't draw a very good ellipse, so it really doesn't get too much closer until it's at perihelion. Now the magnet's pointing away from the sun overall, and the planet is pushed outwards, 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 away, 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 until we're down here at the aphelion. So that was from chapter 57. That was Kepler's physical hypothesis for the distances from the sun. So now he talks about a similar physical hypothesis for the latitudes. He says, let's take this magnet again, and now we'll tilt it. Maybe I should put this at an angle to make it easier to see. Yeah, it's just kind of tough in 2 dimensions. Okay, so this marker is pointing up this way. As Mars is moving around, here, compared to the direction from the sun, the marker is pointing up. It's going to push the planet upwards till over here at the middle longitudes, it's up off the page. As we keep moving, it's not able to push it up as high anymore, and the planet falls and falls and falls until it reaches a node here at perihelion. So it would be, in the plane with the ecliptic. As it keeps moving, it's, as the sun, compared to the power of the sun, it's now being pushed down. It's pushing away from the sun, and it sinks, sinks, sinks. Well, you can't see that. Until it sinks to its southern limit down here at the other middle longitude. And it's no longer being pushed down. And here at aphelion, it is again at the limit, because compared to the fiber from the sun, this isn't pointing either up or down in relation to the fiber from the sun. They're perpendicular. I'll write those on here. So that means that for the latitudes, this would be a node. This would be a node. This would be the northern limit. And this would be the southern limit. Well, I'm sorry. They don't have to be the northern and southern limits that way. It depends on whether the magnet's pointing up or pointing down, in addition to pointing towards the sun and away from it to create the distances. So that's his. Are there any questions about that? That's the. I'm not. Yeah, please let me know. Was that clear? Are there questions about that explanation of the physical longitudes?
Yeah, I just have one question. About, it seems like there could be 360 degrees of possibility of the direction of tilt. Are all the planets, are all their orbits inclined with either the perihelion or aphelion below or above on a, an ecliptic?
Yeah, perfect question. No, they're not. When I was describing that, I was saying if it was the same magnet. And Kepler says that's one possibility, or that there's two magnets in the planet, or two magnet-like things. In other words, you might have one that's pointing in one direction that causes the. So now let's make this the ecliptic. So this can be the sun. So as we move like this, we're getting closer. Here we're at perihelion. Now we're getting pushed away down here to aphelion. Well, if the inclination might be pointing in just a totally different direction. It might be pointing over this way or something. So, yeah, perfect question. No, Kepler does not think that they... I mean, he's sort of just thinking out loud here. It's really difficult for him to, show one way or another whether he's right. So if it was the same magnetic principle, then you're right. Then the nodes would be on the apsides, and the limits would be at the middle longitudes. If they're two different orientations that the planet is keeping in mind, two different types of magnetic or similar to magnetic orientations, then they wouldn't line up. Does that answer your question? Does that make sense?
Yeah, they could either all be unique to each other, or they could all have that identical two magnet effects simultaneously.
Yeah, and then between the different planets, let me go over to the paper again here. Between the different planets, they're all different. So let's say, here we've got our sun, and here we've got the. Let's leave out the Earth, since what the Earth's inclination is kind of a tough thing to talk about. So let's say, we got Mars over here. It's got a line of apsides. It's also got, its own nodes, which for Mars do not line up with the apsides. So there's that's the node symbol. Or it looks a lot like Leo. Anyway, so there's Mars, and then Jupiter has got its orbit here. Here's Jupiter's line of apsides, and then Jupiter's got nodes that are over here and here, let's say. So, each planet, based on just what the observations had been, based on what the data was, every planet had a line of apsides in a certain direction. It also had nodes in another direction, and they don't coincide. Here's what, because Kepler's trying to figure out, maybe it's just one magnetic principle, maybe it isn't. And on page 616, he goes through why it does not look like it's one magnet, because the nodes don't line up with the apsides, and the limits don't line up with the middle longitudes. So I'm going to read a paragraph halfway down the page on 616. He says, the last sentence on the paragraph before it. If the nodes were connected to the apsides, I'll put that picture back up here while I'm reading it. You can have the image in mind. If the nodes, and then perihelion and aphelion are apsides. Let me write that too. So they're the two apsides. If the nodes were connected to the apsides and the limits to the middle longitudes, then the diameter of power of this magnet or whatever would be the same in all respects, administering both eccentricity and latitudes. For it was said in chapter 57 that the diameter that causes the eccentricity is directed towards the middle longitudes, while it was just now said that the diameter that causes the latitude is directed towards the limits. Therefore, if the limits were connected to the middle longitudes, both diameters of the magnets would have the same direction, and their positions thus being in agreement, nothing would prevent their being identical. However, the nodes, or intersections with the true ecliptic, do not coincide with the apsides. So where are they? Well, for Mars, the northern limit, you know what, I'm gonna draw these, put these on the paper here so we can look at how far off they are together. Okay, so let's do this. So now here goes specific examples. So for Mars, Sun, say we've got Mars, Jupiter, Saturn, not to scale. Okay. Mars, Jupiter, Saturn. Okay, so he says for Mars, the northern limit is 12 degrees before the aphelion. So we mark on Mars is here, again, totally not to scale. Aphelion, perihelion, and I'll put in blue the other one. He says the northern limit is 12 degrees before aphelion. So this is the limit. That means this is the node. Here's the node. Over here is another limit. Okay. For Jupiter, the northern limit and the apsides, so here's Jupiter. You know what? I'm just going to draw them as if they all have the same line of apsides, even though that's not true. For Jupiter, the northern limit and the apsides coincide exactly. So for Jupiter, here's the limit. Here's the limit. Jupiter, here's a node. Here's a node. For Saturn, the node follows the aphelion by 24 degrees. So here's a node for Saturn. This node is a limit for Saturn. A limit for Saturn. And then for the Moon, everything is interchanged with everything else. So this is what we would have, if this physical hypothesis was true, the nodes would be aligned with the apsides. The limits would be with the middle longitudes. So we should find the nodes up here, the limits here. What do we find? For Mars, it's almost the opposite. We don't have the nodes at the apsides. We have the limits at the apsides. That's pretty far off. At Jupiter, it's as far off as possible. The limits are right at the apsides, and the nodes are at the middle longitudes. So that doesn't work. And then, for Saturn, it looks a little bit like it's more possible. The node is 24 degrees away from the apsis here. So overall, the conclusion Kepler comes to is that this physical idea he has in chapter 63 is just he doesn't rule out the physical cause for the latitudes, but he says it looks like it's not the same diameter of power that causes both the eccentricity or the distance from the sun and the latitude. That if that's caused by some kind of magnetic power, it's got to have two different orientations in it. And so he talks about how difficult that might be for a planet, but he doesn't rule it out as a physical theory. So So Ryan, so they're all over the place. It seems like they don't line up. So much for that idea, probably. But of course, none of these nodes and limits are based on the real ecliptic yet. They're all based on the inclination with the Earth's ecliptic. So perhaps if we saw how they were inclined to the rotation of the sun, maybe things will work out. We'll have to see if he can figure out where that real ecliptic is, and then we can come back to this problem. So, okay, was that okay about the difference between? Any questions about that? About what the how it doesn't match up with the idea of there being one magnet? Okay, guess that was all right. So, okay, so that's chapter 63. He's got a few more where he deals with some more things. I want to read a quote from chapter 66. In chapter 65 and 66, it might seem a little bit unnecessary to us, but in Kepler's day, it would make more sense why he would talk about these. He asks, what's the biggest latitude you might ever observe? For every observation of Mars from the Earth, what's the maximum latitude north that you'll ever get, and what's the maximum latitude south that you will ever get? It turns out that the maximum possible latitude is not at opposition. Now, I want to read this quote. This freaked out Tycho Brahe. Tycho Brahe thought this was so weird, that planets would not have their maximum inclination, maximum latitude at opposition. Because he'd say, well, when we're at opposition, it's very close to each other. Part of his theory of how the latitudes work would have made him expect that that would be the place of maximum latitude. So, yeah, this is what I'll just read you here on page 625, the letter from Tycho Brahe. He says, oh, yeah, he's on page 620, yeah. Tycho says, it's not always reading the quote. Anyway, he says, after opposition, the latitude got bigger. The cause of this needs to be looked into carefully. He said to Kepler, quote, this is remarkable, that the latitudes reach their maximum before or after their opposition to the sun. Because he thought that the inclination changed and was connected to the motion of the sun around the Earth. So for him, it was a big puzzle. And then Kepler writes, this is pretty funny. This is the paragraph spanning 626 to 627. Kepler says, well, the reason that this would appear remarkable in ancient astronomy is chiefly because Ptolemy and his imitators had fabricated the extremely intricate motions of inclination, deviation, and reflection. For since Ptolemy clung to his invention of the epicycle, as soon as he saw that when the planet was at opposition to the sun, and was thus visible, the epicycle went out to one side, he immediately indulged in conjecture, asserting that at conjunction with the sun, even though it's not visible, the epicycle must go out in the other direction. And generally that at conjunction, the epicycle does the opposite of what he observed it to do at opposition. However, this is not discovering the true by observing, but fabricating the observations by a falsely conceived fancy. Ouch. So, Kepler's, his point in including these chapters, I think, is to show how simple his technique is, and why these things that Ptolemy and Tycho Brahe found so confusing are not confusing at all. Then in chapter 67, he proves again that the apparent sun is where it's at, in case you didn't believe him before with his 20 other proofs he's had of that by this point in the book. Basically, the proof is that since the nodes are exactly opposite each other, it means that if you drew a line between the two nodes, that's the inclination, that's the intersection of the planes of the ecliptic and Mars's orbit. And since that line goes right through the actual sun, it doesn't go through the mean sun, because the nodes, the alignment of the line connecting the two nodes has to be the place where the planes come together, and it goes through the apparent sun and not the mean sun. Okay, so then 68 is the really very, very exciting chapter. In chapter 68, he uses some observations to try to figure out where this real ecliptic is. And it is astonishing that he's able to try to do this. So I'll switch over to this other, okay. And then, just a second. There we go. Okay. So let's watch these animated GIFs here. So people had star catalogs. In Ptolemy's day, he had star catalogs. In Tycho Brahe's day, Tycho Brahe had a star catalog. The stars, some of the stars seem to change their position. So these animations show at the winter solstice, it seems like the stars right at the winter solstice, right at Capricorn, seem to be moving south. And at the summer solstice by Cancer, if you compare where Ptolemy said the stars were to where Tycho saw them, Tycho would have said, oh, the stars are moving north. Watch that again. Now, this is pretty exaggerated. It's not like they were moving multiple degrees or anything like that, but okay. In fact, let me, I'm not sure if he gave the number of, okay, Kepler doesn't use the number of degrees anyway, I don't believe. So how would that be explained? Are the stars moving compared to the ecliptic? Kepler says, no, the stars don't move. They're very, very, very far away. The ecliptic's moving. The orbit of the Earth is changing. So what we're seeing here, we're seeing how the, okay, so here's what we know. Every planet's orbit is inclined. It's got a, hey, hold on, let me grab a tool here. Okay, perfect. Okay, so here's the, so let's show two of them. So if this is the ecliptic, right, this is the orbit of the Earth. The orbit of Mars or whatever is it's just terrible, I'm sorry. And you can see how Mars is inclined with comparison to the Earth. I'll just use one of them now. The Mars's orbit is inclined 1 degree and 50 minutes compared to the Earth's, and the nodes move. So it moves, it retrogresses. It moves, I don't know if this is getting mirrored through the camera or it's going the right way, but the if you looked at it as a top, it goes the, wait a minute, I'm sorry, this way, this way. Yeah, right. Okay. So he concludes, he's saying, the place where you see it move the most, the fact that we see this at the solstices means, does that mean, so let me ask you guys, does that mean that the solstices are more where the limits of Earth's orbit is, or is it more where the nodes of Earth's orbit are? Do you have an idea on that? So let me just turn it a little bit. All right. So I'm just adjusting a little bit here. What's moving more, where the node is or at the limit? Which one is changing its inclination more? Not sure if this wonderful video physical demonstration is working. It's not the node. The node, the node's at its peak. If you're a few degrees before or after the limit, if you're a few degrees before or after the limit, your inclination doesn't change that much. At the node is where it's changing most dramatically. So right along here, this region, at the node. So if overall the orbit is changing, right, the part right between me and the camera there, look, now it's hopefully this is clear enough to you. So since the stars are moving northward at the in Cancer, and they're moving southward in Capricorn, then he says, well, that means that the northern limit must be in Aries. If the, think that one through on your own. Aries is 90 degrees to, well, I'll show on the chart, the picture of Oops. Let me show on the zodiac why he would say that. Okay. So he's saying for the Earth, this is summer, and this is winter down here. And these are the nodes. This is where it's changing the most. So he says, since the stars appear to be moving northward, did I get that right? Since the stars are moving north here in Cancer, that means the ecliptic is moving down here in Cancer. Now, is it going down there because does that mean it's tilted this way or it's tilted this way? It says it's because it's tilted this way. The nodes retrogress. The nodes move in this direction. So that would put this as the northern limit. Now, guess what? For the Earth, the apsides are right here. This is the aphelion. This is the perihelion for Earth. And he's saying, what do you know? It really looks like right at the middle longitude, maybe that's the northern limit. It seems possible for the Earth that, you know, there is just this one magnet. They seem to line up pretty well. Now, this is obviously incredibly imprecise. He has only a vague idea of where the node and where the limit are for the Earth's orbit. He just knows that in the summer area and winter at the solstices seems to be the limit, and at the equinoxes, sorry, these get confusing. At the solstices it seems to be the node, and at the equinoxes it seems to be the limit. So here's what he does. He says, okay, you know what? Here's the way to figure it out. Ptolemy made observations. There are other ancient observations. If we can use very old observations of Mars, where Mars was given a latitude with regard to the ecliptic back then we can start to figure out how Mars's orbit has been changing and how the ecliptic has been changing. Maybe we can figure that out. Because he does have an idea of how fast the nodes are moving in his time by comparing, the more recent observations like Copernicus and Tycho Brahe. So what he does is he goes back. This might shock you, but in Ptolemy's entire book, there are 4 observations of Mars. At least ones that include having a latitude. 4 observations of Mars. That's it in the book. It seems kind of surprising, perhaps, that it would be like that, but Ptolemy only included the ones that he used directly. So, unfortunately, the 3 that he had used for building his orbit, the story is very fun to read. I don't want to just go through everything here. If you read through the chapter, you can see how Kepler is painstakingly figuring out, based on some very vague description from Aristotle about someday during an eclipse, Mars was seen near the star in some constellation or another. Kepler went back and figured out during all the years Aristotle was alive when the eclipse could have been, to try to figure out when this observation was made. He's so painstaking, it's incredible. But unfortunately, the one observation from Aristotle, the one from the Chaldeans, and the 4 from Ptolemy, they're just not precise enough for the kind of work that he really wants to do here. And he ends up saying, he says, therefore, as long as we are wanting suitable observations from antiquity, circumstances compel us to leave this discussion of the motion of the nodes, along with many other matters, to posterity, if, indeed, it should please God to vouchsafe the human race a length of time in this world sufficient to work through such remaining questions thoroughly. So, that's for us to do. We've got to, we can do that for him now. So I would actually propose to anybody who would like to do that work. It only takes about 10 minutes and a little bit of Googling. Take a look at the planets. You can find out what their inclination is with regard to. There's several different kinds of new ecliptics that people use today. There is the ecliptic of the rotation of the sun. There is another ecliptic, which is based on the center of mass of the planets, of the solar system as a whole, not just the sun. So compared to those things, you can find out where are the apsides of the planets and where are the nodes and the limits. What are the inclinations of the planets with regard to those real ecliptics, as opposed to the, frankly, totally arbitrary use of the Earth's one? So you can do that yourself and find out if Kepler may have been onto something with this physical idea of the magnet. And that's the that's the end of part 5. So I guess I'd like to see if there's any questions about part 5 in particular. We can also talk about the whole book as a whole, or if anybody would like to give their own idea of a synopsis or a summary of part 5, or things that seemed like they were important from it. If you'd like to try putting any of it into your own words, see how you're thinking about it. Go for it. All right, well, I guess past our moment of silence for our good friend Kepler. So, in the reading guide on this, there's no homework in particular, and we're about to get started on the harmonies. But, in addition to what's come in the previous sections, for this one, I would say, do Kepler a favor and find out for yourself. Just look it up. Find out what he would have loved to have known, but was unable to, and have a look at, find out how inclined is the Earth, how quickly are its nodes moving. Kepler would have loved to have known that, and then look at the inclinations of the other planets. So that will wrap up the new astronomy. To do a summary of the whole book again, I think might take longer than really makes sense in this. And there's the summary video from when we started this series of things. But I kind of can't resist giving just the shortest of summaries. So the new astronomy. What happened in this book? Where did it come from? Kepler wanted to figure out how God thought in the Mysterium Cosmographicum. Why were there the planets that there were? Why did they have the orbits that they did? He couldn't do that if he didn't know what their orbits were, so he had to figure out what their orbits were to even get the right eccentricities and try to go anywhere with his work in the Mysterium, which he took up again in the Harmonies. But in between, of course, he has the new astronomy. He had to figure out all the planets' orbits. Then he had the accuracy to do the kind of work that he did in the Harmonies. He could not have written the Harmonies without having done the work here in the new astronomy. So in part 1, he had showed that the equivalence of the other guys. He showed that using the real sun actually has a meaningful difference. In part 2, he proved that you couldn't use geometry to explain the motion of Mars, and that we have to throw out the equant and circular orbits. In part 3, he showed that the Earth, like all the other planets, moved unevenly. That the general theory that the Earth moved constantly, or the sun, if you thought the sun moved, Kepler proved that wasn't true. The Earth changes its speed. He put forward a physical principle that the planets move quicker when they're nearer the sun. That was the physical reason for the changes in the speeds. Then in part 4, he came back to Mars armed with this physical principle but without any clue of what shape the orbit of Mars took. He put forward a hypothesis that seems a little bit arbitrary, but in the work of trying to implement that hypothesis, the one of Chapter 45, he got, he got a few blind puppies, as he called it, but he also found out some characteristics of the orbit that let him have the insight at the end of Part 4 of a new type of construction and a physical reasoning based on the magnet for why the planet would come in and out at the rate that it did, and he found that, wow, that makes it move in an ellipse. So by the end of Part 4, Kepler had slightly changed his distance law, that the speed was related to the distance, to measuring the speed based on the area swept out. He believed that the planet moved in an ellipse. He showed that Mars moved in an ellipse, that the sun was at a focus of that ellipse, even though he didn't use the word focus in this book. And then, and then in Part 5, he wraps things up with the latitudes, which in the other guy's books, needed a whole section because they treated the latitudes as something, as a fundamentally different and independent kind of motion from the longitude. For Kepler, he just says take the orbit and tilt it, and then you have your latitudes. And that clears up some of the problems other people had. And he pointed the way towards removing that last vestige of geocentrism, the word latitude itself, by laying out how one could try to figure out what the true ecliptic was based on the motion of the sun, and then finally get the Earth out of astronomy altogether and really have a solar system where you understand it in terms of the sun. So that's where we've gone. Now we're, Kepler and we are ready to move into the harmonies. I got a text asking if I could say some more specifics about the harmonies. Not sure if that meant how we're going to be working through it, or about what our program will be on it. I would hesitate to say something that's incorrect about it, but it's going to be structured differently than these new astronomy things have been structured. So there will be workbooks and guides, reading guides, homework to go through to double check and make sure you're getting what's going on. But it won't be as structured in terms of having a specific order or a pace, or trying to keep a large group of people in different places with different schedules, working on the same sections. The harmonies of the world has also got a nice benefit to it, which is that it's to some degree possible to approach it from different directions. It can be very difficult to try to jump into some part of the new astronomy without the preceding ones, because it's it's very intense. But the harmonies, given that he's got, the 5 parts really do take up 5 sort of different kinds of subjects. The lengths in book 1, plane figures in space in book 2, music in 3, the soul that understands everything in 4, and also the soul of the Earth and how it would be affected by celestial phenomena. And then in 5, when he recreates the universe using the precise ideas about the orbits that he only got because of the new astronomy, and bringing music and everything else together. So that's about as specific as I think it makes sense to be right now. We're going to have the kickoff hangout on this on Sunday, and I think in large part a lot of the guides and things will be ready by then, or are already ready by now. That is not to say, if you would at some point in the future, and this goes for you too, YouTube viewers, at any time, if you write back with any responses or questions about the new astronomy, feel free into the future to do that. It's it's an opportunity to learn about it. And I think by the time we get back to, by the time you're at part 5 of the Harmony of the World, you'll end up wanting to do a bit of a review of the new astronomy anyway, because that's where Kepler really gets into the astronomy side in the Harmonies book, and reviews some things about the motions of the planets based on what he had discovered in the new astronomy. So, yeah. All right. So, anything else, or is this it? All right. Well, hearing no objection, this meeting is adjourned. Thanks for joining, and hopefully, if you're watching this on YouTube, this has been a useful series of videos for you. And please get in touch with us, both on the homework and then more generally about what we're up to. Good night.